Hi, my name is Georgios Damaskinos. I'm a PhD student at the PFL, and today I will present you how to select algorithms by exploiting black box recommenders. This is a joint work with Rachid Guerraoui, Erwan, Merrer, and Christoph Neumann. So let's begin by understanding what is the task of algorithm selection and why it's challenging. I'm sure many of you have been using recommendation services from these popular vendors, such as the one shown on the right. The focus of this work is what happens to newcomers, for example, some startup that wants to bootstrap its service and typically has limited budget and data. The first step for bootstrapping the service is to choose a recommendation algorithm. We see here a sort of chronological evolution of different categories of these recommendation algorithms, the latest of which employ mostly machine learning. Now, these categories and these algorithms have the property that there is no one size fits all. Each approach has its advantages and disadvantages, and the best choice depends on the setup. So what does this newcomer do? It typically selects a subset of these candidates, and on the limited data employs some technique such as cross-validation, where it splits the validation set and training set, and employs this technique to tune these algorithms and finally rank them based on some performance metric that will enable the best candidate to be chosen. An important thing to note here is that this ranking is heavily depends on three factors. First, the implementation. We observed that even relatively simple algorithms and their implementation in two open source libraries produces different sets, substantially different sets of recommendations, due to some subtleties in the engineering details of the algorithms. The second is the hyperparameter space. How does the service provide? How does this newcomer tune these algorithms? Does it deploy grid search or random search? Where were the ranges of the values considered? And the third is the evaluation method. How was the data split, or which metric was it used for the ranking? What may actually happen is that the ranking produced on this limited initial dataset might not reflect the ranking on some future data not yet available. For example, the service provider might observe that in the local dataset, algorithm A, candidate A, performs the best, and therefore choose A to deploy it for bootstrapping the service. After some time, it may turn out that another algorithm, C, performs significantly better than A, and therefore the service, the newcomer would have a much better service had he chosen C from the beginning. Adding up to this not robust initial ranking, these two factors of the newcomer come into play. So you have limited budget, in the sense that this newcomer doesn't have a large engineering team that can implement hundreds of algorithms and tune them and test them and so on. At the same time, this newcomer has limited data and thus cannot robustly rank the candidate algorithms based, for example, on cross-validation. So what we talk about in this work is how can we improve this initial ranking, make it more robust and make it closer to the ideal ranking that we would get if we had the data not yet available. So at this point, I hope that the problem we are trying to solve is clear, and why it's challenging is also clear. Before starting with the solution we propose, I will describe how a recommender system works in a high level, so that we are all on the same page. First, we have some users that create the data. This data can be fed into the recommender through some interfaces, either in the form of implicit or in the form of explicit feedback. This is an example of explicit feedback where the users rate items on Amazon. This data is then fed to some database management system and then used for the recommendation algorithms that we mentioned before to create some outputs that are then parsed to some business logic and finally are given back to the users in the form of a ranked list of recommendations. Noteworthy, the user feedback, as I mentioned, can be also implicit, so the users can provide feedback, for example, by scrolling their social media web page or by clicking a video. Now, what is the problem setup as we have seen it so far? We have the newcomer that wants to bootstrap the service and typically has some limited dataset, which we will refer to as the known dataset. The newcomer also has a list of candidate recommendation algorithms that wishes to rank and choose the best performing algorithm to deploy for bootstrapping the service. On the other side, we have some black box recommender that exposes some query API, which is public, and this black box recommender is typically trained on a significantly larger dataset, which we will refer to as the unknown dataset, and that is, of course, not publicly available. What we ask here is whether we can gain something by using an additional dataset, which we will refer to as the query dataset, that will query both the candidate algorithms and the black box. For example, this query dataset can be a corpus of user profiles that rate movies, and this can use the publicly available query API of IMDb and get the recommendations of the IMDb recommender. Now, we make the following assumptions. We assume, of course, that we don't have an unbounded query data size of the query dataset. We have a limited budget. And we also assume that the black box generalizes better than each candidate, meaning that it produces better recommendations than each of our candidates. Given these assumptions, we make the following hypothesis. The distance metric, as we will define it later, reflects the generalizability of the algorithms. For example, if algorithm 1 and the distance of algorithm 1 with a black box is smaller than the distance of algorithm 2 with a black box, this means that algorithm 1 will provide better recommendations than algorithm 2. Based on this intuition, we propose RecRank. RecRank is a tool that computes distances between recommendation algorithms. How does it work in a nutshell? We have two algorithms, algorithm A and algorithm B. This could be, for example, one candidate algorithm and the black box. We feed into both algorithms the same query dataset and get a set of listed recommendations. This is a ranked list of recommendations. We then use a new method that we propose, namely rec2graph, to parse this set of listed recommendations into a graph. Finally, we propose a new method named GraphDist that takes two of these graphs and computes a single value which reflects the distance between algorithm A and B. How does rec2graph works? We add a vertex for each item that has been either recommended or a user provided feedback for this item. We add an edge between two items A and B if item B is at least in one recommendation list triggered by a feedback event for item A. For example, if I'm a user and I rate Godfather 1 and then I get a recommendation for Godfather 2, then we add an edge from Godfather 1 to Godfather 2. The edge is also weighted based on the ranking score such that it reflects multiple recommendations coming from multiple users. Of course, the weights are normalized such that the graphs are comparable. Now, for the second method we propose, namely GraphDist, we take this created graph and we extract some features. The final distance is the L2 norm of the difference of these feature vectors. GraphDist employs a set of features that reflect different properties of the recommender system and are popular metrics for graphs. For example, the betweenness centrality shows how many items are most popular among the recommended ones. The assortativity shows how well connected these popular items are. For features that have more than one value, such as the vertex in degree, we employ multiple statistical values and we transform we basically get the histogram from these values. This results in a total of 31 features. So recall our problem setup. We have the newcomer, has some limited data set, candidate recommendation algorithms that wishes to rank and select the best from. On the other side, we have the black box that is typically trained on a significantly larger dataset, and we ask the question, what can we do with querying this black box? So RecRank comes into play and gives us a distance between each one of these candidates and the black box. So alongside with the ranking that we get from training, from doing this cross-validation procedure on our limited initial dataset, we get the ranking based on the distance with the black box. So the final question arises, how much can we actually get from this in practice? To estimate that, we select a corpus of 19 recommendation algorithms from two popular open source libraries. And here in bold, we denote two instances of the same algorithm, PMF lib and PMF2 lib, which use different configurations. Therefore, we highlight the fact that not only do we have a plethora of recommendation algorithms, but also multiple ways to parameterize them. For our dataset, we use the movie lens dataset that we split chronologically. The first part, the first 5,000 ratings, constitute our known dataset. The second and biggest part, 93,000 ratings, constitute our unknown dataset. And the final 2,000 ratings are our test set, from which we sample 1,000 for our query set. For our setup, we use online training, and in the sense that the ratings appear in a time-based manner, chronologically. We use top 20 recommendations, and to evaluate our algorithms, we use the popular F1 score that incorporates the precision and the recall. As far as the ranking is concerned, for the evaluation, we use the Spearman rank order correlation coefficient. And basically, the larger the value, the closer the value it is to 1, the more similar two rankings are. To compare against the baseline, we introduce a method that we call setDist that directly compares the algorithms from the output. i.e., it doesn't go through this graph representation. It does so by taking the intersection between users and items. So these are the evaluation results. So here we compare the standard cross-validation on the limited known dataset with setDist and RecRank. We compute the Spearman correlation between the output of the ranking, i.e., the output of each method, and the ideal ranking that we would get on the test set. So this is what we want to be similar to. So a larger value for the Spearman correlation means we are closer to the ideal, to the future ranking, and thus better. In this sense, we see that RecRank has a significant boost in terms of performance by 49%, and we also observe that setDist rank gives also a substantial boost. That meaning that just by exploiting this additional ability of querying the black box, we can indeed get better, more robust ranking for our candidate algorithms. The fact that RecRank performs even better shows that the graph representation is indeed helping out. As a final piece of evaluation, I would like to show you what happens to the ranking correlation while we increase our budget, and there is no surprise in the fact that by increasing the budget we get better performance, of course saturating at some point. So to conclude this video, what we present here is RecRank. RecRank is a method to improve the algorithm selection for recommender systems, and for doing so we propose two methods: rec2graph and GraphDist. Our code is open source, and you can ask me any questions you may have in this email. Thank you very much for watching this video.